Hello student, good morning. I am Dr. Ajay Kumar Sinha, Professor of Chemistry. Today I am going to discuss catalysis. Last class I have discussed adsorption and application of adsorption. Now I am going to discuss catalysis. What is the catalysis? First, you have to understand. You might be knowing about the catalysis that it increases the rate of reaction. But now I will tell you details. Potassium chlorate, when heated strongly, decomposes slowly, giving dioxygen, means oxygen gas. The decomposition occurs in the temperature range of 553 to 873 Kelvin, means high temperature. Not 653, 653 Kelvin to 873 Kelvin. This temperature is required for the decomposition of potassium chlorate. And after decomposition, it gives oxygen gas and potassium chloride. Means reaction you can write like this: 2KClO3, it gives 2KCl plus 3O2. Here important thing is that to get this oxygen gas from potassium chlorate, it requires high temperature. Means 653 to 873 Kelvin. This is the high temperature between this. Here, this temperature I told you. However, when a little quantity of manganese dioxide is added, the decomposition takes place at a considerably lower temperature range, that is the 473 Kelvin to 633 Kelvin. Means now temperature requirement is less. In the absence of manganese dioxide, temperature requirement was high, 653 to 873 Kelvin. But now in the presence of manganese dioxide, little quantity of manganese dioxide, if it is added, then now temperature reduced to 473 to 633 Kelvin, and also at a much accelerated rate. Means reaction will take place at accelerated rate, much accelerated rate, fast. The added manganese dioxide remains unchanged with respect to the mass and composition. Whatever quantity of manganese dioxide was added, it remains same after the reaction. Means it does not take part in a chemical reaction. What quantity you will take, that you will get back. In a similar manner, the rate of a number of chemical reactions can be altered by presence of a foreign substance. Then what is this foreign substance? Actually, this foreign substance is actually catalyst. Okay, catalyst is used in a small quantity. The systematic study of the effect of various foreign substances on the rate of chemical reaction was first made by Berzelius, that is a scientist. He has made a study on this catalyst, effect of foreign substance on the rate of chemical reaction. That is in 1835 he studied. In 1835 he suggested the term catalyst for such substances. For the foreign substance, first time Berzelius in 1835 he suggested the term catalyst for such substances. Substances which alter the rate of chemical reaction and themselves remains chemically and quantitatively unchanged after the reaction are known as catalyst. Again you listen, substances which alter the rate of a chemical reaction and themselves remains chemically and quantitatively unchanged after the reaction are known as catalyst. And the phenomena is known as catalysis. Then this I have told about these things, catalysis and catalyst. Promoters. What is the promoters? Promoters are substances that enhance the activity of a catalyst, while poison, what is the poison? Poison decreases the activity of a catalyst. Means poison you can tell as a negative catalyst, and promoters, that is what you are telling, that positive catalyst. Then promoters are substances that enhance the activity of catalyst, and poison decreases the activity of a catalyst. Then mainly catalyst is of three types: positive catalyst, negative catalyst, and auto catalyst. Means during the reaction, if products form and function as a catalyst, then that is called auto catalyst. You have to not add catalyst from the outside. Sometimes product of the reaction function as a catalyst, that is called auto catalyst. Now I have told about this catalyst. Now example I am telling you. For example, in Haber's process, the manufacture of ammonia, molybdenum acts as a promoter. Actually, iron is used as a catalyst, and molybdenum function as a promoter. Okay, then iron is a catalyst, and molybdenum it enhances the activity of catalyst, that is called promoter. Okay, now catalyst actually now broadly divided into two groups. First group is called homogeneous catalysis and second is called heterogeneous. Now one by one I will tell you. Heterogeneous catalysis. Then last class I have given a hint what is the homogeneous and heterogeneous catalysis or catalyst. Then now I will give few examples. But you know what is the homogeneous catalysis? When the reactants and the catalyst are in the same phase, that is the maybe liquid or gas, maybe both liquid, maybe both gas. Okay, means same phase. When the reactants and the catalyst are in the same phase, the process is called homogeneous catalysis, or the process is said to be homogeneous catalysis. Now few examples I am telling you of homogeneous catalysis. First, oxidation of sulfur dioxide into sulfur trioxide. Oxidation of sulfur dioxide into sulfur trioxide with dioxygen in the presence of oxides of nitrogen as the catalyst in the lead chamber process. Lead chamber process, this reaction takes place. Then this is the example of homogeneous catalysis. Why? Because here sulfur dioxide is gas plus oxygen, SO2 plus O2. 2SO2 plus O2, both are gas, and it gives 2SO3 in the presence of catalyst, means NO. Nitric oxide, here it functions as a catalyst. This is also gas. Then reactants are gas, and product is also gas. Then this is the examples of homogeneous catalysis. Both are in the same phase, reactants. Here SO2 and O2 both are reactants, and catalyst is NO. Then all three are in gaseous phase, same phase, and it is giving 2SO3, sulfur trioxide. Hence balanced equation you can tell 2SO2 plus O2, it gives 2SO3, and catalyst is NO gas. The reaction, the reactant sulfur dioxide and oxygen, and the catalyst nitric oxide are all in the same phase. Second example I am telling you, hydrolysis of methyl acetate. Hydrolysis of methyl acetate is catalyzed by H plus ions furnished by hydrochloric acid. Hydrochloric acid actually it is used, then that will furnish H plus. Then here you can say methyl acetate is liquid and hydrolysis is going on. That's why reaction will take place with H2O, means methyl acetate plus H2O. Then here methyl acetate is liquid, water is liquid, and catalyst is hydrogen ion. Okay, HCl means it provides H ion. Then all are here in liquid state, and after the reaction, after the hydrolysis of methyl acetate, it gives two products, acetic acid and methyl alcohol. Here all reactants are also liquid, products are also liquid, and catalyst is also liquid, that is the HCl. HCl provides a H ion. Then here reactants and the catalyst both are in the same phase, means both are in liquid phase. Third example I want to tell you, hydrolysis of sugar. Hydrolysis of sugar is catalyzed by H ions furnished by sulfuric acid. Here in this reaction, this sugar means sucrose C12H22O11. C12H22O11, that is a common sugar. Okay, then common sugar solution plus H2O. Then here both are in liquid state, sugar solution plus H2O, and here little quantity of H2SO4 you are adding. This is also liquid. Then here reactants and catalyst, H2SO4 provides H plus. Then now all reactants and catalyst both are in same phase, means liquid. Then here you can say this is the, you can say means hydrolysis of sugar is again examples of homogeneous catalysis, and this reaction gives two products, glucose and fructose, both are in solution form. Then glucose formula C6H12O6, and fructose is same formula C6H12O6, and both are isomer. Then this is the example of homogeneous catalysis. Okay. Now I am coming for this heterogeneous catalysis. Okay. Heterogeneous catalysis. Then here hetero means different. Hetero means different. Means reactants. Reactants, maybe 2 reactant, maybe 3 reactant. And reactants you can tell. Reactants and catalyst both will be different phase. Both will be in different phase. Okay. Then here the catalytic process in which the reactants and the catalyst are in different phases is known as heterogeneous catalysis. Okay. The catalytic process in which the reactants and catalyst are in different process is known as heterogeneous catalysis. Example I am telling you, oxidation of sulfur dioxide into sulfur trioxide in the presence of platinum. This example I told you in the case of homogeneous also. SO2 converted to SO3 in presence of oxygen. Here directly SO2 is converting to SO3, but in the presence of platinum solid. Platinum is solid. Then in the first example what I discussed in the case of homogeneous, there 2SO2 plus O2 was there and it has given 2SO3 in presence of NO gas, nitric oxide. But here directly 2SO2 is converting into 2SO3. 2SO2 is converting into 2SO3 in presence of platinum. Then here SO2 gas, that is the gases for platinum, is solid. And this is the example of heterogeneous catalysis. The reactant is in the gaseous state while the catalyst is in the solid state. Hence it is the example of heterogeneous catalysis. Now next example I am telling you, that is the combination between nitrogen and hydrogen. You know that nitrogen and hydrogen, when it reacts, it gives ammonia gas. Combination between nitrogen and hydrogen to form ammonia is in the presence of finely divided iron. Finely divided iron in Haber process. Process name is Haber. Because question is asked, which catalyst is used and what is the name of process is asked. Then here formation of ammonia gas from nitrogen and hydrogen, it requires finely divided iron. Then here iron is solid, nitrogen and hydrogen both are reactants, are in gaseous phase. Then this is the example of heterogeneous catalysis. And N2 gas plus 3H2 gas, it will give ammonia gas. Means here all reactant and products are gaseous phase and catalyst is in solid phase. The reactants are in gaseous state while the catalyst is in the solid state. Next example I am telling you, that is the oxidation of ammonia into nitric oxide in the presence of platinum gauge in Oswald process. Okay, this process name is Oswald. Then here you can see ammonia gas is converting into, that means oxidation you are talking, oxidation of ammonia into nitric oxide, NO. Nitric oxide means NO in the presence of platinum gauge in Oswald process is the example of heterogeneous catalysis. Then reaction you can write 4NH3 plus 5O2, both are gas, and catalyst is platinum, that is solid, and it is giving 4NO2 plus 6H2O. 6H2O means here gaseous form, vapor form, and NO is also in a vapor form. Then here also you are saying that both reactant and both products are in gaseous state and catalyst is in solid state. But here you should remember that reactants and catalyst must be in different state. Okay, sometimes product may not be the, you can say this things, gas may be different from reactant, product may be different from reactants phase, but always it should require for the heterogeneous reactant and catalyst must be in different phase. Next example I am telling you, hydrogenation of vegetable oil. Hydrogenation of vegetable oil in the presence of finely divided nickel. This is very, very important reaction. Okay. Then here any fatty vegetable oil you can tell, vegetable oil, and this vegetable oil that is in a liquid form, vegetable oil plus hydrogen gas, because you are doing hydrogenation. Actually vegetable oil, this is unsaturated, double bonds are present, double bond, sometimes maybe triple bond also. Then now this double or triple bond present in vegetable oil, that will become saturated in presence of hydrogen gas, bond will break. Suppose double bond is there, then one bond will break and two hydrogen will join. Then now double bond became single bond, means saturated. Even if triple bond is there, then two bond will break, two pi bond will break. In double bond only one pi bond is there, one sigma bond is there, but in triple bond two pi bond is there, one sigma bond. Then one bond will break pi bond, and it will make two bond with hydrogen, H, CH and CH. Okay, and here in triple bond, then two bond will break, two pi bond will break, then when one pi bond will break, it will combine with two hydrogen, two bond with hydrogen will make. Then here two pi bond is breaking, means four hydrogen. Then now it is called saturated. Now unsaturated is becoming saturated, and that time it is called this example I am telling you, that product vegetable oil plus hydrogen in the presence of nickel. Nickel is solid, finely divided nickel means powdered form, but it is a solid. It gives a, we can say, saturated compound, that is called vegetable ghee, banaspati ghee, what you are telling. Now it is not available, but example I am telling you, vegetable ghee. This is the solid form. It is giving solid form. Then here see, vegetable oil is in liquid form. Hydrogen gas is there. Vegetable oil a liquid form plus hydrogen gas. Okay, and in presence of, actually this I am talking about hydrogen gas is going to be added. Then here vegetable oil is in liquid form, and nickel is in solid form. Okay, and it gives vegetable ghee, solid. Okay, then this is the example of this heterogeneous catalysis. One of the reactant is in liquid state and the other is in gaseous state. At least reactant, any one reactant, actually here hetero means all are, you can see, different only. Vegetable oil is liquid, hydrogen is gas, and catalyst is solid. All are in three phases. That's why it is hetero, not the same phase. Then one of the reactants is in liquid state and the other is in gaseous state, while the catalyst is in the solid state. Then this I have discussed about the catalyst, homogeneous and heterogeneous catalyst. Now I am going to discuss adsorption theory of heterogeneous catalysis. What are the theory behind heterogeneous catalysis, that I am going to discuss. Then here adsorption theory is there. Adsorption theory of heterogeneous catalysis. Then now I will tell about this theory. This theory explains the mechanism of heterogeneous catalyst. The old theory, simply it is called adsorption theory of catalysis. But now new name is given as a mechanism of heterogeneous catalysis. And old name, that is simply adsorption theory of catalysis. This was what was the old theory? First to take idea. This adsorption theory of catalysis, means old theory, was that reactants in gaseous state or in solutions are adsorbed on the surface of solid catalyst. The increase in concentration of the reactants on the surface increases the rate of reaction. This is according to the old theory. The increase in concentration of the reactants on the surface of reactant increases the rate of reaction. Adsorption being an exothermic process, already I have discussed. Adsorption being an exothermic process, the heat of adsorption is utilized in enhancing the rate of reaction, because it is providing heat, and you know that rate of reaction increases with increase of heat, hence the rate of reaction increases. The catalytic action can be explained in terms of intermediate compound formation. Here you understand, the catalytic action can be explained in terms of intermediate compound formation, the theory of which already I have discussed. Now I am telling the mechanism. The modern adsorption theory, now you understand modern. Old you understood. The modern adsorption theory is the combination of intermediate compound formation theory and the old adsorption theory. If we will combine both theory, means old theory plus combination of intermediate compound formation theory. How intermediates are formed? Before giving the product, intermediate products are formed temporarily for a short period. Then that theory is called, that is the intermediate compound formation theory, and the old adsorption theory, if both you will combine intermediate compound formation theory plus old adsorption theory, then you will get modern adsorption theory. The catalytic activity is a localized on the surface of catalyst. Then mechanism, what are the mechanisms? Then there are 5 steps. Then what are that 5 steps? I am telling you. First step, diffusion of reactants on the surface of catalyst. This is the first step. Diffusion of reactants to surface of the catalyst, first step. Second, adsorption of reactant molecules on the surface of the catalyst. This is the second step, means adsorption. Adsorption of reactant molecules on the surface of catalyst. Okay. Diffusion is the first step, just diffused. Just like you are going somewhere, after reaching there you will do something. Then that going there is just like a diffusion. And after that, just like you went somewhere, now you will meet some person. You will meet some person. That is the second step, adsorption of reactant molecules on the surface of the catalyst. Okay. Now, these molecules will reach to the surface of catalyst. Third, after meeting the person, you will talk. You will see the person. Now you will tell about your purpose. Then here, third step is like that. Occurrence of chemical reaction on the catalyst surface through formation of intermediates. Okay. Intermediate will be formed, means now he will talk. He will talk to the person. He will talk to the person. That is actually here you can tell chemical reaction. Chemical reaction on the catalyst surface through formation of intermediate. Now intermediate is formed. Now fourth step, desorption of reaction products from catalyst surface. This desorption, after that now you have talked. You have talked to the person. Then what will you do? After that he will tell something, your work will be done or not. Suppose your work is done, means product formed. Then like that way, fourth step, you can tell desorption of reaction products. Product is formed. Okay, desorption of products formed from the catalyst surface. Okay, and thereby making the surface available again for more reaction to occur. Means now you met the person, you talked, and your work is done. Means product is formed. Then after that what will happen? You will, suppose you are in queue, then you will go, other will get a chance, then other is like that way, new reactant. Okay, it will go on the surface of catalyst. Okay, then means if you will leave, product will leave, then reactant again, new reactant will come, again same thing will repeat. And fifth step, diffusion of reaction products away from the catalyst surface. Actually, that time just from the your work is done, and from the queue you came out, but you are only there. You are only near that person. But now only just from the queue you were in queue, now you came out. Then after that you will go outside, you will return to your home. Then this is the fifth step. Diffusion of reaction products away from the catalyst surface. Okay, then this all 5 steps I have told you. Okay, first diffusion, second adsorption, third occurrence of chemical reaction, fourth desorption of reaction products, and fifth diffusion of reaction products away from the catalyst surface. Okay, the surface of the catalyst, just to know more, the surface of the catalyst, unlike inner part of the bulk. Okay, actually any you can say solid, you will see the inside. I told you that every side forces will be cancelled out, but upper portion of the solid, it will be unbalanced. It is not, forces are not cancelled. That's why adsorption takes place. It wants to attract, because they are inside, it is neutral. All forces are cancelling to each other, because in north side, south side, east side, west side, equal forces are working. Only direction is opposite, hence it is cancelled. North side, south side, equal forces are working. Then that forces will be cancelled. Then all forces will be cancelled. But upper molecules, solids upper molecules, it is not balanced. Only from the inside that forces are acting on the molecules of upper surface. Correct? Then that's why it has a tendency, natural tendency to attract the out foreign materials like a gas, and it will attract. That is called adsorption. Then here I am talking about that things that the surface of catalyst, unlike the inner part of the bulk, has free valences or valences, you can tell, which protect these things. This free upper, I am talking about the surface of the catalyst have free valences which provide the seat for chemical forces of attraction. When a gas comes in contact with such a surface, its molecules are held up there due to loose chemical combination, because it will attract. Then attraction, force of attraction, attractive force, that is actually called bond, but that attraction, there less attraction, hence weak bond it will form, means loose chemical combination will take place. If different molecules are adsorbed side by side, suppose now one type of molecules adsorbed, A molecules adsorbed, only there side by side other molecules like B is adsorbing, then what will happen? Because all are adsorbing, different molecules are adsorbing nearby, just like you can say neighboring molecules, you can tell. Then both A and B will adsorb on the surface of catalyst, and then after that what will happen? After that they may react with each other, resulting in the formation of new molecules. Then now they will form new molecules, they will make bond, that bond will be a strong bond. Thus formed molecules may evaporate, leaving the surface, because in the beginning it was the weak bond, then new bond formed, then old bond will break. Weak bond was whatever big bond was there, that will be broken and product will evaporate, leaving the surface for the fresh reaction molecules. Other reaction molecules may come. Like that way, a small quantity of catalyst you will require, and because they will make the product and it will leave, it will go from the surface of catalyst. Hence the same catalyst, from the same catalyst, little quantity of catalyst you can say give too much product. Only a small quantity, surface area should be more. Then this I have told you about the this what happens during the reaction. This theory explains why the catalyst remains unchanged in mass and chemical composition at the end of reaction, and is, I can say, very, very effective, because now I told you that after making the bond, they are making big bond, and after when both are reacting, A and B, and they are making product and they are leaving the place, that bond, product bond is strong and weak. This is the weak bond. They are forming in the beginning weak bond, that bond breaks, then they are not reacting with the catalyst, Correct? Quantity is same, composition is same. Composition of catalyst is same. Okay. Now, if they will go, product will go, the new reactant will come. Okay. Then this I told you that even in a small quantities, it will be this a small quantity of catalyst. This will be active efficiency will be there. It will be very effective. A small quantity of catalyst will be also very effective. Okay. This but one thing here know that this does not explain, this theory does not explain the action of catalytic promoters and catalytic poison. This theory, remember question is asked, does not explain the action of catalytic promoter and catalytic poison. Sometimes if you want to enhance the this things, rate of reaction, then in the with a catalyst something is added, then that what something is added that helps in enhancing the rate of reaction. Rate of reaction means helping the catalyst, that is called promoter. And sometimes if you want to reduce the rate of reaction, then again some extra material is added that poison the rate of reaction, means it will come slow. Then this theory does not tell about the these things, how they are doing, how means catalytic action of catalytic promotion and catalytic poisons. It is not explaining about that things. Now I am telling about the important feature of solid catalyst. What are the you can say characteristics, important feature or characteristics of solid catalyst? Then there are two important features. First, you can say important feature is activity and second is selectivity. There are two features, important feature of solid catalyst. Okay. Then I am talking about now, I can say activity. The activity of catalyst. The activity of catalyst depends upon the strength of chemical eruption to a large extent. Chemical eruption is mainly responsible for the activity. The reaction must be absorbed reasonably strongly on the catalyst to become active. Means quantity I am talking about, the reactants must be absorbed reasonably on the catalyst to become active. However, they must not get absorbed so strongly that they are immobilized, means they can't move. They should not make very strong bond. It should make loose bond only. They must not get absorbed on this. They should not get absorbed so strongly that they are immobilized, and other reactants are left with no space on the catalyst surface for adsorption. Should make a weak bond so that easily it should react with neighboring, and after that products should go outside and it should give the space for the new reactant. Okay, this is necessary. It has been found that for hydrogenation reaction, the catalytic activity increases from group 5th to group 11 metals. Group 5th metal, 6 metals, 7 metals, group 5th, group 6, 7, 8, 9, 10, 11. These metals are actively increases the catalytic action. Catalytic activity increases from group 5th to group 11th metals, with maximum activity being shown by group 7 to 9 elements of the periodic table. Okay, group 7 and 8, 7, 8, 9, they are showing too much, you can say, maximum you can tell activity. Maximum activity being shown by group 7 to 9. Group 7, 8, 9. Okay. Now, one example I am telling you, that 2H2 plus O2. 2H2 plus O2, it will form water. It is very easy this reaction. Hydrogen plus oxygen gas. It gives water vapor or liquid, you can tell. 2H2 plus O2 gas. Both are gas, and platinum is solid. Platinum is solid, it is giving 2H2O liquid. Then this is the example of activity. Now comes second, selectivity. Selectivity means here choice. All catalyst you can say will not work for all reaction. It is a specific catalyst is used. One catalyst is used only for one reaction, particularly enzyme. Enzyme I will come, that time I will discuss. But here selectivity means here they are specific in action. The selectivity of a catalyst is the ability to direct a reaction to yield a particular product, new product. All will not give the same product. Okay, the selectivity of a catalyst is the ability to direct a reaction to yield a particular product. For example, starting with H2 and carbon monoxide. Just to see, now reactants are same. H2 and you are considering H2 gas and carbon monoxide. These are the reactant, and you are changing different catalyst. Catalysts are different, then they will give different product. Reactants are same, CO plus H2. 3 example I will tell you. CO plus H2. In all, CO plus H2 is there, but product are giving different in presence of different catalyst. When catalyst is nickel, CO plus 3H2, both are gas. Nickel is catalyst, solid, then it is giving two product, methane gas plus H2O vapor. See, CO plus 3H2. Now again CO plus 2H2 is there, 2H2. Then reactants are carbon monoxide and H2 only. And now catalyst is copper. Copper in presence of ZnO and chromium oxide. Three are there. Copper is there, ZnO and Cr2O3 is there. Then now in presence of this catalyst, means copper in presence of ZnO, Cr2O3, it gives methyl alcohol. See, in the beginning it was giving methane gas plus H2O, water. Now here same reactants, it is giving methyl alcohol, gaseous form. Now third, again you can see carbon monoxide and hydrogen is there, means CO plus H2, CO gas plus H2 gas. Now in presence of copper catalyst, it is giving formaldehyde, HCHO. Now see, catalyst changed, product changed. That's why it is called selectivity of a catalyst. Okay, this is a choice. All reaction wants a special type of catalyst. Reactants are same, but we will change this catalyst, product will be different. Thus it can be inferred that, we can tell that, the action of catalyst is highly selective to highly selective in nature, you can tell. Highly selective in nature. Okay, that is a given substance can act as a catalyst only in a particular reaction and not for all the reaction. Same catalyst you can't use for the different type of reaction. Okay, not for all the reaction. This is very important point. A given substance can act as a catalyst only in a particular reaction and not for all the reaction. It means that a substance which acts as a catalyst in one reaction may fail to catalyze another reaction. Okay, this I have discussed about the these things, characteristics, or you can say important feature of solid catalyst. Now I am coming towards the safe selective catalysis by zeolites. Zeolites, very important question. ZEOLITES, zeolites. Zeolites is a catalyst. Okay, ZEOLITES, zeolites is a catalyst. Then this is actually safe selective catalysis by zeolite. It will not work everywhere in a particular shape. It depends upon particular shape. That's why it is called safe selective catalysis by zeolites. This is very important. I want to discuss a little more. The catalytic reaction that depends upon the pore structure, small hole, pore structure of the catalyst and the size of reactant and product molecules is called safe selective catalysis. Okay, the catalytic reaction that depends upon the pore structure of the catalyst and the size of the reactant and products molecule is called safe selective catalysis. Zeolites are good safe selective catalyst. Zeolite, okay, good safe selective catalyst. Because why? Because of their honeycomb like structure. You remember, question is asked. Its shape is honeycomb bees you have seen, like that you remember that thing. Honeycomb like structure. They are microporous. Honeycomb you might have seen where bees are sitting, that is just like a round. That type of shape is there. Honeycomb like structure. They are micropores. They are microporous, you can tell. They are microporous and aluminosilicate. They are microporous aluminosilicate with three-dimensional network of silicate in which some silicon atoms are replaced by aluminum atoms, giving aluminum oxygen silicon framework. Means in that structure, that honeycomb like structure you will see, then that actual structure is made from aluminosilicate. Length, breadth, height, all are there. That is called three-dimensional network of silicates in which some silicon atoms are replaced by aluminum atoms, and they will make bond. Oxygen will be in the middle, one side aluminum, other side silicon. Okay, this framework, oxygen will be in the middle and one side aluminum, other side silicon. This type of bond they will make, means aluminum oxygen silicon framework. The reaction taking place in zeolite depend upon the size and shape of reactant and products molecules, as well as upon the pores and cavities of zeolites. Little gap may be there in zeolite. Then in that a small hole, and this cavities, this is also responsible. Both it depends the size and shape of the reactant and product molecules, as well as upon the pores and cavities of the zeolites. Okay. Then this action depends on all the things. They are found in nature. Actually, this honeycomb already said in a natural way it forms. Sometimes synthetically also it is formed. They are formed in nature as well as synthesized for catalytic selectivity. Synthesized means it is made, okay, artificially by chemical reaction. Zeolites are being very widely used as catalyst in petrochemical industry for cracking of hydrocarbon and isomerization. For that purpose, zeolite is used in petrochemical industries. For what purpose? Then for cracking of hydrocarbons and isomerization. An important zeolite catalyst used in the petroleum industries is ZSM5. Okay, remember it is the name of catalyst, geocatalyst. Z, capital Z, capital S, capital M, 5. Okay, ZSM5. Okay, it converts alcohols directly into gasoline. Gasoline means petrol. See the use. ZSM5, that is a zeolite catalyst. It will convert alcohols directly into petrol, means gasoline, by dehydration them to give a mixture of hydrocarbons. Petrol is what? Petrol is a mixture of hydrocarbon, but number of carbons are less. Okay, petrol is only hardly, you can say 3 carbon, C2, C4. This carbon will be less number. Hydrogen will be, obviously it will satisfy. Then that is called actually petrol, mixture of hydrocarbons. Then this I have told you about the zeolite. Now this today I am stopping only here, because now again enzyme catalysis is there. It will take more time. Okay, that's why I will discuss separately in next class. Thank you.